Okay, today I'm just going to give you a very quick, brief overview of regression assumption testing and regression diagnostics. You'll need this information for the Tuesday tutorial. Because of the Easter break, we just haven't had time to cover this, and our tutorials fall before the lecture. So it's just a very brief overview. You'll practice the techniques in the tutorial, and then we'll pick up on Friday and cover it in more detail. So I think you're probably all familiar with the assumption of normality. It's one of the core assumptions of all statistical tests that you've encountered, and it's common to the tests that you're familiar with, like the t-test, the ANOVA, the correlation, and we also need it for a regression. So the ANOVA and regression are actually fairly robust against mild to moderate violations of this assumption. So if there's a little bit of skewness, it's not something to worry about. You just note for the reader and then move on. Where it's a problem, though, is where there's moderate to severe skewness. And that can affect the conclusions that we draw. So in those cases, we might take corrective action such as a data transformation. And we'll pick up on that in more detail on Friday. Alright, the reason that they present an issue is that they actually affect statistical power. And so that's a concept that we introduced in 1003. It's the likelihood of finding a significant effect if there really is an effect in the underlying population. And so your conclusions may be driven by outliers or problematic scores. So one of the assumptions of regression is that you have some error. So there's this error term here. That's the error in your regression equation. Now we can't do anything directly to the error, as it's what's left over after fitting the regression line. So the y hat or predicted y. And you'll always have error. It's a normal part of statistical analysis. But what we can do is see whether there's a systematic pattern to that error, i.e. the residuals. So if there is a pattern, it's non-random, then this will affect the conclusions that we draw from the data. If we're going to have error, we're quite happy with a randomly distributed error, but we don't want systematic error. Okay, so you can see here your regression line, and we've got each individual data point, and the difference between each data point and the line is our residuals. Okay. Alright, so the regression assumptions are actually made about these residuals. The residuals should be normally distributed with a mean of 0. So, in other words, if they're completely random, they will be as many points above the regression line as below, and the average distance of the residuals will have a mean of 0. Now, another assumption that we have is homoscedasticity, which we'll cover in a moment, but it's basically about the variance of the residuals. And then we have independence of errors, so the residuals are uncorrelated with y. And the final assumption is linearity, which I think you're quite familiar with now in 1003 with scatter plots. You look at for a linear pattern. So if we want to examine these assumptions, we actually look at these three here using the regression syntax, and we generate a series of graphs that show us the pattern of the residuals. Now, linearity of the relationship, well, we use scatter plots for each individual predictor to test that. Now, if we want to have the benefits of regression to answer our research question, then we have to pay the cost of ensuring that the data meets these underlying assumptions. If it doesn't, then we may not draw the correct conclusion. Alright, so I'll cover this in more detail on Friday, but basically we don't want there to be a systematic pattern to the residuals. We want it to be nice and random in the scattering. Anything else means that there might be a problem. Alright, so if it's truly random, then the residuals will be normally distributed with a mean of 0. It's often said that it's centred around 0. So we've got here a nice graph. You can see here, this is from the GRE data set that we looked at in the lectures. You see there we've got a regression line there, and it's going to look pretty tricky, but I'm going to twist it 90 degrees on its side there. And I'm going to overlay here now. We can see the residuals, they're the data points that are above or below. And I'm going to overlay that there with the normal distribution. So if I get out my little laser pointer, each of these data points, so from down to here, you can see that they're all falling nice and normally along that distribution. We don't have any points out here, so if we had a data point out here, we could see that that would really not be normally distributed, it would be an outlier. So that's what we're looking at with the assumption of normality. Now, if the pattern of residuals are normally distributed, then even a moderate violation of normality for your predictor or for the dependent variable is not going to be a huge issue. But if they are strongly skewed, so there's a lot more on the right-hand side, below the regression line, or a lot more on the left, above, then this is an issue to tell the reader about, and they will need to interpret their results or conclusions cautiously. So we call this the assumption of normality of residuals. And we can actually generate a histogram, which you'll do in the tutorials, to actually have a look at the distribution. So you can see here that our z-scores, this is -1, -2, and you can see most of our data points fall within negative or positive 2, and it's nice and normally distributed. The only one that might be a little bit problematic is this one out here. Now we can also inspect the pattern of residuals by looking at the scatter plot for the regression model. Now this is different from the scatter plots you've seen before, where you consider the relationship of a single predictor to a criterion. And what this does is it considers all of the predictors in a multiple regression, and it gives the standardized residual. So anything that's greater than maybe 2 might be a little bit problematic. You can see here we've got a few data points, but there's certainly none that are greater than positive or negative 3. Another assumption, and we're looking at the same graph here as before, a scatter plot, but I've got a stylized version of it, is this thing called homoscedasticity. So in a homoscedastic distribution, we've got the same amount of error variance, so the height of the highest to the lowest, for all levels of the predicted values. So you can see here we've got as much error variance here as we do down there. Now, the larger this range, of course, the worse the prediction is. What we want is something that's nice and random. What we don't want is something like this, where you can see you've got a lot of error variance here at low values of the predictor and relatively small error variance here at medium to high. So the question you'd be asking is, why is the prediction worse over here than down there? And the reason is, more often than not, is that there's skew in one of the predictors. But sometimes, even without skewness, you can still see a heteroscedastic distribution. And again, that would be something you would want to tell the reader about. So we get that by having a look again at this scatter plot. Now the following discussion will deal with the situation in which inspection of the residual plot suggests that one or more regression assumptions have been violated. So perhaps you have a heteroscedastic distribution, perhaps you have a whole lot of error variance in one part of your scatter plot, and we want to see what we can do about it. So short of using a different statistical procedure, no one wants that, we have two courses of action open to us. We may find that one or more outlying data points on one or more variables are unduly influencing the regression analysis, and potentially they're leading to an erroneous conclusion. So we might want to ping them or exclude them, drop them out from the analysis, and then report with those data points excluded. We're very reluctant to do this though, because we want to give an accurate impression of the sample that we collected. But in some cases it's unavoidable. And the other option is when one of your predictors deviate greatly from normality, so skewness and kurtosis, we can actually apply a data transformation, which you'll see how to do in the tutorial. So what we do is replace the actual variable with the transformed one in the regression. So for example, we might take the square root of particular scores. Certain data transformations may alleviate skewness, but it's very hit and miss, and sometimes it can make the pattern worse. So we're very reluctant to transform data, and it would only be if it affected the normality of the residuals, or if it affected homoscedasticity. Alright, so now on to the topic of regression diagnostics, which you'll be doing in the tutes. One of the problems with regression is that a particular score or two can exert an undue influence on our model. So 2 or perhaps 3 residuals might alter the course of the regression line, either making it steeper or making it shallower. So we perform regression diagnostics to inspect the influence of these problem scores. So we can expect the univariate outliers, so looking at box plots. We can expect the residual statistics. You can actually save them in SPSS. Looking for anything greater than 3 standard deviations, either above or below the regression line. And then we can inspect what we call a multivariate outlier. So instead of looking at one variable, it sees whether the variable is unusual on all of the predictors in your data set. And we do this by using this thing called Mahalanobis distance. So Mahalanobis distance is difficult to spell. It's named after Indian mathematician P.C. Mahalanobis. That's him. And it's an indication of how far away an observed score is from what we would expect based on its predictors. If the score deviates substantially, well, it doesn't follow the pattern, and it will actually influence the regression line. And we can generate this Mahalanobis distance for every participant in the data set. And if it deviates substantially, that would be bad, so we want to try to avoid that. And we'll often, not always, but often remove them if they distort our model. Okay, so how do we identify what's a good or a bad Mahalanobis distance? Well, we know if it deviates substantially, it'll influence the regression line. How do we know when we should draw the cutoff? Well, instead of getting a z-score, our Mahalanobis distance is based on a chi-squared distribution. And we look for a chi-squared corresponding to a p-value less than 0.001. Our degrees of freedom in the chi-squared analysis is based on the number of predictors. So this is probably the easiest thing you'll do in this course. If you have 4 predictors, your degrees of freedom, you guessed it, will be 4. If you have 3 predictors, your degrees of freedom will be 3. Nice and easy. So I'll give you an example of 3 predictors. We're going to go down here to the row that says 3. There we go. I want to evaluate at the 0.001 level, and so the cutoff that we use is 16.27. If any of our participants are higher than 16.27, then what we're going to do is we're going to exclude them. Or perhaps we might just use a filter variable just to take them out temporarily, see whether or not they actually affect the regression equation. If they don't, then we're more likely to just retain them. Okay, so 16.27 is our cutoff. So in this week's tutorial, we'll be testing those regression assumptions in SPSS, and we'll be having a look at regression diagnostics. And then I'll pick up on these issues in the lecture, and we'll take it from there. Okay, enjoy.